Let's take a look at how latency and throughput come together in the memory system. And we're going to start out by looking at the memory system of a CPU. So when we look at latency and throughput, memory access is going to be a big issue. And all programs need to access memory, but they have very different approaches depending on the type of hardware. So as we've seen before, CPUs are focused on latencies, GPU on throughput. Now let's take a look at how this comes into play in the actual memory system. So here we are for a CPU, and we're going to see what happens with memory. So we've got a bunch of instructions in our program here. You can see what they're doing. We're doing some addition, we're doing a load, we're doing another load here. Now the CPU is going to spend a lot of effort to look at these instructions and analyze them and figure out what the dependencies are here. So this instruction needs B from the first instruction, this instruction needs E from the third instruction, but this one doesn't need any of that, so we can go ahead and mix them up. Let's take a look at what it takes to do this. So here's our processor we saw before. If we look at the core, we've got this part over here, we're doing our processing. All of this area down here, this area down here is the area that we spend energy on and effort on analyzing the instructions. So this part of the chip here is going to analyze the instructions to figure out which ones we can do at the same time. So then we've got some processing units inside here, so we've got some ability to do operations, so addition and load and store, and then we're going to use this part of the chip to figure out which operations we can do together. So we go ahead and start off. We found out we can do these two instructions at the same time. So we go ahead and start them. We do the addition and the adder, and we do the load store and the load store unit. Now we go ahead and do this, but it's going to take a long time to access our main memory. So main memory takes about 100 cycles to go and access. It's really slow compared to the processor. So what we do about this is we're going to go ahead and we're going to put in a cache. So we've got this level 1 cache, which is going to keep recently used data, and we're going to send this load over to the cache to see if the data is there. So remember the picture we had of the chip before? Here's the core, here's the part we do the processing in the pipeline. This part up here, this is the level 1 cache in the processor. Okay, so if we find the data in the cache, that is a hit, that's great. We can send the data right back, and while we're waiting on this data, we can go ahead and do another instruction, because we've got all this analysis in the processor figuring out which instructions we can do in parallel. So that's great. We keep going along. Now we finished up those instructions. We get another 2 instructions, doing lots of work here. This load, we're going to see if it hits in the cache. Whoops, it didn't hit in the cache. So what are we going to do? This load didn't hit in the L1 cache. How should we handle it? Well, basically, if some cache was good, then more cache is probably better. So we're going to go ahead here and we're going to add some more cache to this. We're going to put on an L2 cache that's enormously larger, means it's going to be slower, and we're going to hope that we find our data there. So here's our processor again. Here's the part we were working on. Here's our L1 cache. Now here's the L2 cache. So this is the part that we've added on now. If we hit in the cache, that's great. And if we don't, we do the same thing again. We say, let's find an even bigger cache. Now there's no more room in the processor core here, but if you look at the whole chip, we've got a huge chunk of the chip here for the cache. So we've got this huge middle part of the chip here is just the L3 cache. So we've now got lots and lots of space on our chip used up by caches here. But they take a long time. So if we hit in the L2 cache here, we're going to wait about 20 cycles to get the data back. So here we go. We're going to take a long time. We're going to get our data back. Finally, we get our data back. We can finish that instruction, and we can go ahead and do the next instruction. And this one had to wait because it needed the data for that instruction. So what do we see here? We have lots of fancy hardware in the CPU to try and reduce latency, make things happen faster. And we're reducing the latency through these caches and through getting better throughput by the ability to have multiple instructions at the same time. But this takes a lot of hardware in the processor to figure this all out. And the key to getting good performance on the processor is if you can make the cache work for you, you get good performance, low latency. So if you're writing code that you want to run on a CPU and you want it to run fast, the most important thing to focus on is how can you make the cache work well? How can you make sure your data is in these closer caches so you get low latency and good performance?